Hi everyone. I've received a few requests to go over the basics of concurrency in Haskell, so I thought I'd put together this very short video to just go over some of the key concepts that you've studied in this course to give you a brief reminder of the kind of key ideas. So what we're going to do is consider a setup where we have two or more processes that are going to run in parallel. So that's going to be different pieces of code running at the same time, but they're going to communicate with each other. So this is a concurrent program. We're going to have independent computations which could run at the same time, and then they interact with each other via some way of synchronizing or communicating. Now, what we've studied in this course is the use of channels in Haskell as that means to do the communication. So channels are a data structure that we can then share between these different processes and then use that data structure to communicate between them. So the setup is going to look a bit like this. The idea of this very basic ASCII process diagram is that we're going to have a client or some clients. They're going to send requests to a server process, and the server is going to make responses back to the client. And we're going to use Haskell's interface for channels, provided by the control.concurrent library, which is built in, provided with GHC Haskell implementation, and it has the following functions, which we're going to use for doing communication and concurrency. Now, just a key thing to say at the start here, so you'll notice that all of these functions return something of type IO. So this is the IO data type, which we use to abstract the notion of a side effectful computation in Haskell. So going out of the kind of pure mathematical world to computations that actually can change our execution context and produce some side effects. So all of the concurrent work that we're doing here is going to produce things using the IO type. So we're going to be using the do notation as a way of giving us some syntactic sugar to work with that. I'll very briefly recap again the sort of more direct way of using combinators to combine together these IO computations, but we can use the do notation to simplify things for us. So we can read IO, we can read something of type IOA as a side effectful computation that does some kind of input-output side effects. Actually, it could do lots of different kinds of side effects. And running that computation produces some value of type A inside of it, which we then want to use the operations to sequence together and push take that A and use it in some future computation. You can read it as we do some side effects and that produces something of type A. So the relevant functions, we've got newChan that creates a new channel and of type A. So this is a channel with which we can send and receive values of type A. We're creating that data structure so that we can then share it between the client and the server. WriteChan is how we send on that channel. So we take a particular channel who has payload type A, and we take an A, and then it sends it over the channel, and that gives us back this result that tells us, well, this has done some IO computation to do this writing to the channel. Reading, we take a channel of type A. We're going to wait until there is something on the channel. This is a blocking operation. We have to wait till there's something there, and once there is something there, then we get that return back wrapped in this IO computation. So that's how we receive. So that's how we do communication. And then this last operation here, fork IO, is the key thing to take a piece of code, take an IO computation, and then run it in its own thread as a separate piece of code that's running in parallel that could then interact with other pieces of code. So we take an IO unit computation, we spawn off a new thread, a new process that we can then that is then running on its own independently and then can interact with the rest of the system. We get back an IO thread ID, that's the identifier for the thread, but we won't need that here. Okay, so I'm just going to split that off and have this on the side so we can kind of keep an eye on it. I'm going to progressively work through a few examples and make them more interesting as we go. So we're going to be working with the IO type. This also has the structure of a monad, but you don't necessarily have to think in the sort of general monadic terms to understand what's going on. The main thing with IO is that we need some operations to help us sequence together things that these IO computations. So we have the sequence operator that takes an IO computation that produces an A, an IO computation that produces a B, runs those in sequence, so does the first one followed by the second one, and so the result that we get is this kind of compound IO computation, which produces the B at the end. So it ignores the return result of that computation. The bind operator is like the generalization of that says, okay, we start off with the first I/O computation that we want to run, and we run it, we evaluate it, those side effects happen, and then we get this A out, and we pass it to a function that's expecting this A, but it's this pure A now. We've run it, the side effects has happened, and we've got out this A. We give it to this function, and it applies that function with the A, and that produces some other I/O computation of type IOB, which depends now on that A, and our return result is IOB. So you can think of that as sequencing. Again, it's like the semicolon in C++ or C or Java. It's do this thing, then do that thing, but we have the flow of data between it. We have the result of this computation being given to the second computation, which can depend on it to calculate its results. So let's start by making our server. We need a channel, and we're going to start very simply with a channel that just has type unit. This is the singleton type, has only one constructor, so it doesn't contain any information at the moment. We're just going to kind of see it as like it's almost like a ping, like do something, but there's no information in that request, and that's an IO unit computation. So we want to read from this channel. I'm going to call the channel from client, because we're going to be receiving from the client. So we want to read from that channel. That's going to give us back an IO unit. We don't care about that information, so I'm going to just use the sequence and sequence that with something saying I've got a request. So we receive from the channel, and then we print out a little message on the terminal. Let's write a client then that has access to a channel and uses it. So I'm going to call that channel toServer. We're going to write on that channel, we're going to write the unit type. So I've got, right chan. So I've got my channel of type chan unit. So in this case, the A type is being instantiated to unit. So we're giving it a payload of the unit value, and it's going and doing that. So I've described what the server is going to do as a function. I've described what the client's going to do as a function. Now I need to put them together. So I'm going to call this my setup function, and setup is going to use fork IO. We're going to fork, no, we're not. We're going to do new chan first. We need to create a channel and share it between the client and server so that they can interact. So I'm going to do new channel, and I'm going to use my bind, which is going to give me access to this channel. I'll just call it C there. And I'm going to fork server 0, but with that channel C. So that's going to run the server C function with that input channel. It's going to take that computation, create a thread using the runtime system, which might interact with the operating system, create a parallel running piece of code, which is our server. And so that goes off, and fork IO kind of returns back to us the thread ID, and this server is now running. And it's waiting for requests. So after doing that, I'm going to run my client with that channel. So I've got a sequence of things: create a new channel, fork off the server, run the client. So that looks like it type checks. Let's run that. So the code runs, it finishes, and we see this message, I got a request. That's come from the server, and that's happened because the client has sent it a message, and it has then received that message. Didn't contain any information, it was just the unit value, but it triggered that response. Okay, so at this point, I'm going to clean things up a little bit and use the do notation, because using the sequence and the bind quickly gets horrible and ugly. So recall that we can use the do notation to clean this up, where instead of using the bind operator, we can put in this little left arrow thing here, which is like doing this bind, but it desugars it for us into these operations. So we can say run this computation, new chan, and use the bind operator internally and bind the pure thing inside to C. So C will have type here chan of unit. So then I can do fork IO, and then I can do client 0. So remember, in the do notation, we can think of this now like an imperative program. It's a sequence of steps. Each one of these things in the sequence has to be an IO computation. This is an IO thread ID. We could put something in here to bind that thread ID. Now X has type thread ID, as we can see in the little tooltip there, but actually for our purposes in this example, we don't need to know that information. So I'm just going to remove that. I'll keep that little hint in there for the moment. Similarly, I could take this, use the do notation. Remember, they have to be starting at the same column. And okay, that's the same program. We haven't done anything drastic here. It has the same behavior. What was interesting here when I ran this is I could see we get this nice thing. This happens in concurrent programming. The GHCI shell inserted the message GHCI angle bracket space, but that kind of overlapped with the server writing out this message, I got a request. And so that's going to probably keep happening in these examples, because if we have multiple parallel computations running who are writing out messages to the console, well, they're going to kind of get smushed on top of each other if they're happening at the same time. So this is not a problem. This is not something going wrong. It's just the confusing thing about concurrent programming. When they're doing side effects, they can have these sort of overlapping behaviors. At least we can read this and understand what's going on. Right, so let's do two clients. Let's actually use fork again and fork off this client that's going to run here in parallel to the main execution, and another one. And this is complaining because that puts out an IO thread ID, and I said that this was going to be an IO unit. So I can use the return function. Remember, return has the type for the monad class. It goes A to MA. So in this case, we're thinking of return for the IO type that goes A to IO A. So that lets us create a trivially side effectful computation, injecting this value into it, this pure value. So that gives us this type that we wanted. So now I've forked off three processes, the server and two clients. So let's see what happens. Perhaps you can think for a second what you expect to happen. Okay, what we see is I got a request, again interleaved with the prompt. But maybe we were thinking we were going to expect there to be two of these messages, because we have two clients now. We used the client function twice. That started two separate clients applying this function and creating two different computations that interact with the server. So why did we only get one message? Well, the fact is that our server zero definition, it reads from the channel once, it outputs that message, and then it terminates. That's the end of the computation. There was nothing here saying that the server should keep going. Okay, so let me change it so that it's recursive. We're going to do a recursive call here. So this is a server that's going to run forever and keep listening to requests on this channel and just go round and round and round like this. It's never going to terminate, it's just going to keep receiving requests. So if I run again, okay, now we see the two messages. I got a request, I got a request. Great, so that server process is still running, never mind. I think my computer can handle a few bonus processes that are going to be sitting there until I shut down GHCI. That gives us the template of the idea. Right, let's make things more interesting. So far we haven't actually transferred any information between the client and the server. I'm going to copy the code and rename these variables here and do a new version of this where the clients actually now send some information. So we'll have two clients again and two servers, that sounds fine. But let's change the channels so that instead of unit, they're actually sending integers. So when we read from a channel, now the bit of data that we get out is going to be interesting. This n is going to be an int, machine int, and I'm going to say, I got a request, and I'm going to show that integer. And then we're going to go back round like this from here. This should be server 1. And so the client, that's going to have a channel of which we can send and receive integers, and I'm going to write the value 1. And in fact, let's have it do multiple things. Let's have it write 1 and then write 2. Okay, so this new channel now, when we create it, it's going to have the type chan int. Haskell infers the type there that it knows it's going to have to be a channel in which it can communicate integers. So we're sporting off all those 3 things. That should all work out. Let's see what happens. Good. So now we see that the server is picking up that bit of information. It got a request of 1, it got a request of 2, got a request of 1, got a request of 2. So it's getting a little bit more interesting. So why don't we do something a little bit more now, where the server actually counts sums up the integers that it has received as it goes. So we're going to add another parameter to server 1 to act as a kind of storage within the server. Notice at the moment how we start off server 1 with this channel, and it retains that channel by recursion. It does this recursive call, and so it retains the knowledge of this channel, that it has access to this channel throughout its lifetime. It keeps going. So we can add some extra parameters. I'm going to call this total, and so this is going to be our total of requests that we've seen so far. We'll still print that out there, but I'm going to add here in the recursive call n plus total. So once we've received a request, when we recurse, our total is now equal to the n plus the previous total. So we're sort of learning this information as we go. Each recursive call, we're going to get a bit more added on. And yeah, let's leave it at that for the moment. I mean, I could say let total prime, that's going to be the new total. Let's do this. I got a request, and total is now, and we can show that total. That's getting a little bit long, so I'm just going to break that here. And of course we need to show on that as well. So we work out what the new total is, total prime. We do this print here, and yeah, okay, thanks. And then we recurse. So the client stays the same. It's the server that's changed. Now we see down here that we need to kick off the recursion with the initial total. This server 1 expects another parameter now. It expects its initial total, which we'll set as 0. Great. So the server got a request of 1. The total is now 1. It got a request of 2. The total is now 3. It got another request of 1. The total is now 4. Request of 2. The total is now 6. So we see that the server now has this memory of this integer via this parameter here as well. Of course, it's not actually mutating a piece of data, but this is a sort of functional pattern for us having a server that retains some state, and it does it via the recursion. Okay, so far, going back to our little picture, all we've got are requests. The client requests to the server, and the server learns some information. Let's do responses now. So in order to have a response, I need to have some extra piece of, I could use that channel again to communicate back, but that's going to conflict with other requests coming from other clients. So I'm actually going to introduce a type here, which I'm going to call the request type, and I'm going to have my requests be a pair. At the moment, the requests are integers, so it's like this, but I'm going to actually pair the integer with another channel, which is going to be the type of the response. And let's have that response be an integer. So the idea is that the client is going to send an integer, and it's going to send a channel on which the server can then respond back to that specific client. Otherwise, the server doesn't know which client it's going to respond to. The channel, as it is, we've shared that amongst lots of clients. So the server's receiving requests on that channel, but it doesn't know which client it's come from. So it doesn't know who to respond to. If the server just wrote back to that channel, then anyone could see it. But we want to localize the interaction between a particular client and the server. So the client's going to do that by sending the server a channel on which it can respond. So now, when we read from the channel, we're going to get a pair of an integer and another channel. I'm going to call that resp channel for response. And rather than printing out now, I'm actually going to use that response channel and I'm going to write onto it with that current total. So I'm going to write total prime on there. So let me just put in some comments to remind us what's happening. Get a request from the client. Calculate our new total. Communicate, or let's say respond to the client with that total, and repeat. So now our clients have to do a little bit more work. So I'm going to create a channel in the client. I'm going to call it resp channel for response channel. And then when I do my writing, I'm giving it the pair of that integer and that channel. Now actually I get a response on that channel, so let me actually read from it. That's going to be the response coming from the server. I'll call that T for total, and then I'll output that. I just say got T. So we do a request by creating a channel. That's going to be where the responses come on. And to the server, we send the pair of that integer and the response channel. We read that response, get the response, and do something with it. So I have a feeling that I probably want to turn this into a function, because this is going to be kind of a little bit of a common pattern, I guess. So I'm going to call this the sort of request response on a particular channel, which is taking that, and I guess what I want to get back is the response value. Of course, that's going to be an IO. We're in the IO monad. So request response, I want to basically be this kind of pattern here. And in fact, I need to have a payload that I want to send. So create a new channel, do that request, make a request with n, get the response, and then yeah, that's what we return back. So I've just made a little function to kind of do this pattern for me of sending the response with the new channel and then reading back sending the request and reading back what the response is. So down here now I can do T request response 1 like that, and I can do another one, T request response 2, and yeah, let's print that out as well. So our client is making a couple of requests again, but it's hearing back from the server now. And then finally, we can put it all together. These are the second version of this. And the only difference that we need to deal with is, I should have put that there, that's the request type. Let's just follow through with these errors. Oh, of course, we forgot to give the server there. My apologies. Okay, so this is our helper function for client making a request and receiving a response. So we've got our server, we've got our clients, and we've got our setup. Let's rock and roll. So the client, we see we got 2, that's a running total, got 1, got 4, got 6. What's interesting is that they're kind of coming in a funny order here. That's the joys of concurrency. It's going to be non-deterministic as well, and we get all these kind of interesting different kinds of interleavings here. So I think one of those clients is sometimes seeing the total as 1 first, before the other one sees it as 2, and we get all kinds of possibilities. But in the end, 1 plus 2 plus 1 plus 2 in whatever kind of order gives us 6. Okay, let's do a final thing now. I'm going to make it a little bit fancy just one last time. I want this server to eventually stop. So hopefully you've been following on so far. We're going to do just one last thing to this, and that's going to add a little bit more structure to what we're doing. So rather than our requests being like this, actually, sorry, I'm going to edit this. No, I'll keep that so I can send you this file later. I'm going to make a data type called command. And that's going to be represent our requests, and we're going to have two things in here. Either we can have a command from a client, which is a pair of an integer and a response. Or we can request to stop, and that will shut down our server. So now when we read the channel, we're getting a command, and I need to do a case on it. So in the case that we're looking at an add, then we're going to respond to the client just like we did before in that computation here, and still do the recursion for server 3. But if we get stop, then we're going to just give out our final total. And that's going to end the recursion. So our requests now have a little bit more structure to them. We can differentiate two different kinds of requests, either an add request or a stop request. Now, I don't need that, we've got that already. The client, I'm going to keep the client the same. That's going to make these requests. Of course, what we need to do now is change this. Actually, we do need to change our request and response. Apologies. So let's get this back. Let me call this request and response command, because here we want to do the add command. So we've just got a custom data structure basically. So these are commands. So that's all pretty much the same though. We've just introduced a data structure, but it's isomorphic in this constructor to the pair. Now, there's going to be something interesting that's going to happen in a moment. So let's just check that we're all ready. This is a command channel. So the first time we run this, it's going to behave not as expected. And let me just get all those types right. So what we might think is that we'll see the one thing I forgot is the stop command. So far it should behave basically as we had before, so let's try it out. Yeah, looks the same. Got 2, got 1, got 4, got 6. Yeah, those are the totals, but we don't see this final total thing here because we need to actually have something send that stop command. And actually what I'm going to do is send that from the main thread of execution here, send that stop signal. So the final total was 0 and nothing else happened. Perhaps that's what you expected, perhaps that's not what you expected. Well, let's remember that these computations are being forked off and they're immediately returning. We're not waiting for the server to finish, we're not waiting for the clients to finish. Fork.io is going and starting that as a separate independent running piece of computation, and it's returning back, and these things are then going off and running in parallel, and then we're going and executing here. And what's happening is that on line 167, when we write stop onto the channel, the server's seeing that and it's stopping. It's stopping the world before the clients can even do the rest of their work. So even before one of these clients has gone in a request, this request has come in first and we've stopped everything. The end. Now maybe that's not what we want. Maybe we want the clients to do their thing first and then this to happen. So we could put that into one of the clients. What I'm going to do is just make this code one little level of extra fanciness and have the client report back when they're finished. So I'm going to make a new channel called the signal channel, and I'm going to make sure that each one of the clients has access to it. Now I don't need to communicate any information other than just one bit of information, but what I'm going to do is have this signal channel be such that I can write a unit to it when I'm done. So each one of these clients is going to get the signal channel, and then I'm going to wait for the clients to finish their work by receiving on that channel twice. So I'm going to read that unit and I'm going to do it twice, like this. And only then am I going to send the stop signal. So we've started off the server, we started off the clients, but this main thread of execution inside of setup 3, is going to stop here, waiting for something to be received on signal. That's going to come from one of these clients, I don't know which. Then we're going to proceed, receive another one of those signals, and then we can do the stop to the server. And there we go. We have the interactions within the clients, and we see that the final total was 6. Great. So I'm going to stop things there. Hopefully that gave you a good recap. As an exercise to the reader, why don't you go and generalize the idea of having clients, multiple clients signaling back to a main process by having a function that starts n clients and then does some other I/O action once all n of those clients has finished. So you'll need to parameterize that by some integer n, some function that generates clients, and some piece of code to run once all of the clients are done. And so we'll need to repeat the forking and repeat this reading back on the channel with the signal n times. It's a little bit more of an advanced exercise. It's just putting together the things here, but with kind of generalizing from just 2 clients to many, where that number of clients is a parameter which you can then change. Okay, good luck with your exam.